Welcome to our quantum deep dive.
Great to be here.
Today we're diving straight into, well, the really fascinating work of John Stewart Bell. We're drawing on Yurgo Schneppe's essay.
Right, it's a great piece.
And our mission, basically, is to unpack Bell's theorem, its groundbreaking stuff, understand the experiments that confirmed its, frankly, mind-bending predictions.
Definitely mind-bending.
And see how it's kind of fueling this whole quantum tech revolution happening now.
Mm-hmm.
So think of this as your shortcut, your express route to grasping one of the really pivotal ideas in modern physics.
Absolutely. And Schnepp's essay really nails Bell's impact. He was born in Belfast in 1928, a theoretical physicist.
Okay.
And he was really driven by this deep curiosity about, the basic logic of nature, the fundamental laws.
Right.
He worked at the UK Atomic Energy Authority first, then later moved to CERN.
CERN, okay.
And it was in his 1964 paper. This was the one looking at the Einstein-Podolsky-Rosen paradox, the EPR paradox.
Yes.
That's where he introduced his revolutionary Bell Theorem.
Okay, so Einstein, Podolsky, Rosen, EPR. They weren't totally sold on quantum mechanics as it stood, were they? They felt something was maybe missing.
That's exactly it. Yeah, they felt quantum mechanics might be incomplete. They suggested there could be some underlying factors, deterministic factors. People call them hidden variables.
Hidden variables, okay.
Yeah, things that would explain why quantum events seem probabilistic, but in a way that kind of fits better with our everyday world, a predictable local world.
Local meaning things only affect their immediate surroundings.
Pretty much, yeah. No instantaneous influence across distances. But what Bell did, and this was just ingenious, was to show that no local hidden variable theory could ever actually reproduce all the predictions of quantum mechanics.
Oh, so he put a mathematical constraint on it.
Exactly, which implies something really fundamental. Non-locality might just be baked into how the universe works.
Wow. So this wasn't just philosophers arguing then. Bell actually gave scientists a tool, a way to test these ideas.
Absolutely. That's the crucial part. The Bell Theorem gave us a measurable inequality. Think of it like a threshold.
Yeah.
If the world worked the way Einstein hoped, with local hidden variables, then the correlations you measure between distant particles couldn't be stronger than a specific limit set by this inequality.
Right.
Bell showed quantum mechanics predicts correlations can be stronger. They violate that limit.
So it became an experimental question. Go measure it.
Precisely. It gave experimentalists a clear target. Test this inequality. See if reality follows local realism or quantum mechanics.
And this wasn't some, obscure theoretical point. You mentioned Bell's insights paved the way for actual technologies.
Oh, absolutely fundamental. Bell's work is really a cornerstone of modern quantum physics, and it's directly led to the whole field of quantum technologies.
Like quantum computing.
Quantum computing, yeah. Secure quantum communication, quantum cryptography, all that stuff, by letting us experimentally test the limits of classical ideas like realism and locality.
Realism being things having properties even if we don't look.
Right. He basically opened the door to actually harnessing the sheer weirdness of quantum mechanics for practical purposes.
Okay, to really appreciate why Bell's work was such a big deal, maybe we should quickly recap the context. Quantum mechanics didn't just appear fully formed, right?
Not at all, no. The early 20th century was, a whirlwind of new ideas.
Yeah.
You had Planck in 1900 talking about energy coming in discrete packets, quanta.
The start of it all.
Then Einstein used that idea to explain the photoelectric effect, talking about light quantiphotons. And the Bohr-Sommerfeld model gave us an early quantized picture of the atom.
But those were still early steps. The full theory came later.
Exactly. The 1920s were the key period. That's when quantum mechanics, as we really know it today, was formulated. You had Heisenberg's matrix mechanics.
And Schrödinger's wave mechanics.
Right, with the absolutely fundamental Schrödinger equation describing how quantum states evolve.
Yeah.
It's central.
Still gives me chills seeing it.
Yeah. And then Dirac brilliantly unified quantum mechanics with special relativity in his theory of the electron.
So an incredibly successful theory emerged. But even then, there were these, weird aspects that bothered people, even the founders. Schnepp's essay mentions these paradoxes.
Oh, yeah. Big ones, like the measurement problem. Schrödinger's cat is the famous example.
The simultaneously alive and dead cat.
Until you look. It highlights this bizarre idea that measurement itself seems to collapse a state from superposition into a definite outcome.
And Heisenberg's uncertainty principle.
Right. The idea that you fundamentally can't know certain pairs of properties perfectly at the same time, like position and momentum, there's a limit.
Yeah.
Delta X, C dot, delta P, get track bar. It's not about bad equipment. It's fundamental.
Which brings us back to Einstein and the EPR paper in 35. That spooky action at a distance really troubled him.
Deeply. Einstein, Podolsky, and Rosen looked at entanglement, these instantaneous correlations between distant particles, and basically said, hang on, this can't be the whole story.
It seemed to violate locality, the idea nothing travels faster than light.
Exactly. That's the spooky part.
Yeah.
So they argued quantum mechanics must be incomplete. There had to be a more complete theory, probably with these hidden variables.
The ones Bell later tackled.
Right. Hidden variables that would explain these correlations locally and realistically. Realism meaning particles have definite properties all along.
So for Einstein, quantum mechanics was like a statistical approximation of a deeper, more classical reality.
That was essentially his view, yeah.
Yeah.
He felt the theory without hidden variables just couldn't be the final word. And this is exactly the debate Bell stepped into.
Okay, so Bell wasn't just picking a side in the Einstein-Bohr debate. He asked a different kind of question.
A much sharper question, really. Bell asked, could a local hidden variable theory even exist mathematically without contradicting quantum mechanics itself?
Yeah, okay. Could you even construct such a theory?
Right. And his huge contribution was the Bell Theorem. He formulated a specific mathematical inequality, a test that any theory based on local hidden variables must obey.
And the punchline was?
He showed mathematically that standard quantum mechanics predicts violations of this inequality in certain setups.
So they couldn't both be right.
Exactly. If quantum mechanics is correct, and experiment after experiment suggested it was, then reality itself must be non-local. At least local realism had to go.
Which, as you said, gave experimentalists something concrete to test. Schneppat mentions Elaine Aspect's work being key here.
Crucial. Aspect's experiments really put it to the test.
Let's dig into Bell's theorem itself a bit more there. What's the core idea in simple terms?
Okay, so at its heart, Bell's theorem basically says you can't have both locality and realism, as we classically understand them, and still perfectly match all the predictions of quantum mechanics.
Locality being no faster than light influences, realism being properties exist before measurement.
Exactly. Those two very reasonable sounding assumptions, when you combine them mathematically, lead to this constraint, the Bell inequality.
But quantum mechanics predicts things that break that constraint.
Precisely. So if quantum mechanics holds up, you have to give up either locality or realism, or maybe even both in their classical sense.
And where do the hidden variables fit in again?
Well, hidden variables were the proposed way to save local realism. The hope was maybe there are these unseen factors, the un of the math, like PAB lambda, that determine the outcomes deterministically.
So quantum randomness wouldn't be truly random.
Right. But Bell showed that local hidden variables, ones that respect that locality principle, simply can't explain the strong correlations predicted by quantum mechanics. Any hidden variable theory compatible with quantum results would have to be non-local itself.
Schneppat's essay mentions the math, like the CHSH inequality. Can we get a feel for that without, doing the whole calculation?
Sure. Imagine you have those two entangled particles, again, sent to Alice and Bob far apart. They each choose one of two measurement settings. Let's say A for Alice, B for Bob. Local realism puts a limit on how correlated their results can be across different combinations of settings. The CHSH inequality, which is a specific form, says a certain combination of these correlations, like EAB plus EAB plus EABB, can't be greater than 2.
A hard limit of 2.
If local realism holds. But quantum mechanics predicts that for entangled particles, this value can actually reach 2, which is about 2.8, clearly bigger than 2.
So the math shows a clear gap between local realism and quantum mechanics.
A clear, testable gap. The experiments are designed to measure that combination of correlations and see if it stays below 2 or goes above it.
And if the experiments find correlations greater than 2...
It's strong evidence against local realism. It tells us nature is, stranger than our classical intuition suggests. It points towards that fundamental non-locality, this deep connection between entangled particles.
That really is a profound consequence. It shakes up our basic picture of space and causality.
It absolutely does. It challenges how we think reality is structured. But this non-locality, this entanglement, it isn't just weird. It's turning out to be a resource, a key ingredient for these new quantum technologies.
Which brings us nicely to the experiments Schneppat discusses, the ones that actually went out and measured these correlations.
Right. The goal was clear. Generate entangled particles, measure them far apart, and see if the correlations violate Bell's inequality. And as Schneppet emphasizes, Elaine Aspect's experiments in the 1980s were absolutely groundbreaking.
What was so special about Aspect's setup?
Aspect and his team used entangled photons. But the really clever part was how they changed the measurement settings, the orientation of their polarization detectors.
How so?
They used fast optical switches to change the detector settings after the photons had left the source and were already in flight, heading toward the detectors.
Whoa! Why was that important?
It addressed a key loophole, the locality loophole, sometimes called the communication loophole. If the settings were fixed beforehand, you could imagine the particles somehow coordinating their results via hidden signals when they were created.
Ah, like a prearranged agreement.
Exactly. But by changing the settings randomly and super fast while the photons were separated, it became incredibly hard, basically impossible, for any signal traveling at light speed or slower to coordinate the results. It really tested locality.
Okay, so what did Aspect find? Did the correlations break the limit?
They did. Significantly. The results showed a clear violation of the Bell inequalities, consistent with the predictions of quantum mechanics, not local realism. It was powerful evidence for quantum mechanics and non-locality.
That sounds pretty decisive. But Schneppet mentions later experiments, too. Were there still lingering doubts or things to improve?
Well, science is always about tightening things up. While Aspect's work was huge, people pointed out potential, albeit maybe unlikely, loopholes. The main ones were the detection loophole, and ensuring the locality loophole was really closed.
Detection loophole? What's that?
It arises if your detectors aren't perfectly efficient, if they miss some particles. The worry is, maybe the particles you do detect aren't a fair sample. Maybe if you could detect all of them, the correlations would actually satisfy Bell's inequality.
Okay, so you need very good detectors. And the locality one needed even more rigorous tests.
Right, making sure there was absolutely no possibility, however remote, of any slower-than-light communication between the measurement stations influencing the outcomes.
So have these loopholes been closed now?
Yes, that's been a major focus. Schneppet points to 2015 as a landmark year. Several independent teams conducted experiments using different systems, entangled photons, electrons, even atoms and diamond defects that simultaneously closed both the detection and locality loopholes.
Loophole-free tests?
Loophole-free Bell tests, exactly.
Wow.
And they all confirmed the violation of Bell inequalities with very high confidence. People are also now doing these tests in systems relevant to quantum computing, like superconducting circuits.
So the verdict from experiments is pretty overwhelming now. Quantum non-locality is real.
The evidence is extremely compelling. These experiments show that the way quantum mechanics describes reality is fundamentally incompatible with our classical ideas of local causes and definite properties. Entangled particles really do seem to share this connection that defies classical explanation.
And confirming that is vital for building trust in the quantum phenomena that underpin these new technologies.
Absolutely crucial. You need to know the resource you're trying to exploit, entanglement. Non-locality actually behaves the way the theory says it does.
Okay, let's talk more about entanglement itself then. Schneppet covers its role in technology. Can you break down what entanglement actually is?
Sure. So, imagine you create two particles, photons, electrons, whatever, in a special link state. Entangled. Their properties become interdependent.
Interdependent how?
It means if you measure a property of one particle, say its spin or polarization, you instantly know the corresponding property of the other one. Instantly. No matter how far apart they are. Schneppet gives that typical state notation like frac, swan, +1 Rengel, d Euler Rengel. If you measure particle A and find it in state 0, you know B is in state 1, and vice versa.
Even if B is on the moon?
Even if B is on the moon. It's this shared fate, this perfect correlation, or sometimes perfect anti-correlation, that's so strange and powerful.
And Bell's work was key to actually using this.
Totally. Before Bell, entanglement was mostly seen as a philosophical puzzle, part of the EPR paradox. Bell's theorem, and the experiments confirming it, showed non-locality was real. It wasn't just a weird feature of the math. It was a feature of reality. That gave people the confidence and the theoretical tools to think about how to exploit it.
So where is entanglement actually being applied now?
Schneppet mentions quantum communication and cryptography as prime examples. Quantum key distribution, or QKD, often uses entangled photons.
How does that work for security?
Well, if Alice and Bob share entangled particles to generate a secret key, any eavesdropper trying to intercept and measure the particles will inevitably disturb the entanglement. That disturbance can be detected.
So eavesdropping leaves a trace.
An unavoidable trace, according to quantum mechanics. It offers potentially unbreakable security based on fundamental physics, not just computational difficulty.
That sounds incredibly useful. What about quantum computing?
Entanglement is also crucial there. Qubits, the quantum version of bits, can be in superpositions of 0 and 1. But when you entangle multiple qubits, they form a complex, interconnected state.
Which lets them do more powerful calculations.
Exponentially more powerful for certain problems. The entanglement allows the computer to explore a vast number of possibilities simultaneously. Schneepat mentions Shor's algorithm for factoring large numbers, which could break current encryption, and Grover's algorithm for searching. Entanglement is key to their power.
And quantum teleportation. Still sounds like sci-fi.
It does. But it's real. It's about transferring the quantum state of a particle from one location to another, using entanglement as a channel.
So you're not beaming the particle itself, Scotty style.
No, not the matter. You're transferring its precise quantum information, its state, onto another particle at the destination. You need entanglement and some classical communication to make it work.
Schneepat gives some examples of progress. What's happening on the ground?
Well, in QKD, there are commercial systems available. And we've seen impressive demonstrations like China's Mush's satellite distributing keys over thousands of kilometers, as Schneepat notes.
Wow. Satellite QKD.
Yeah. In quantum computing, companies like IBM, Google, Rigetti, and many others are building increasingly large and capable quantum processors. You can even access some via the cloud.
Like IBM's Q experience.
Exactly. And quantum teleportation has been achieved over significant distances, hundreds of kilometers in optical fiber, and even between islands. These aren't just lab curiosities anymore. They're becoming real engineered systems.
Bell really did unlock a whole new domain. Okay, finally, Schneepat touches on the deeper philosophical side and the debates Bell stirred up.
Right. Bell's theorem didn't just impact physics. It hit philosophy hard, too. It fundamentally challenged deterministic worldviews.
Because it suggested randomness is inherent.
It certainly strengthened the case that the probabilistic nature of quantum mechanics isn't just due to ignorance, like flipping a coin, but might be a fundamental feature of reality. At least, local deterministic explanations were ruled out.
So it forced people to grapple with big questions about reality itself.
Absolutely. Questions about realism? Do things have definite properties when we're not looking? Bell's work suggests maybe not, or at least not the way we thought. In Nonlocality, what does this instantaneous connection mean for our understanding of space, time, and causality?
How does cause and effect work if something here can instantly correlate with something over there?
It's a deep question. It doesn't seem to allow faster than light signaling, which is crucial, but the correlation itself is instantaneous. It raises profound questions about the nature of physical influence.
And not everyone accepted the implications straightforwardly. There were alternative interpretations.
Oh, definitely. Schneepat mentions David Bohm's interpretation, Bohmian mechanics. It is deterministic and realistic, but it achieves this by introducing a non-local quantum potential that guides particles. So it accepts non-locality up front.
Okay, so it keeps determinism, but sacrifices locality.
In a sense, yes. Then you have interpretations inspired by Niels Bohr and the Copenhagen view, which basically say stop asking about properties before measurement. Physics is about what we can measure.
Focus on the results.
Right. And others, like the many worlds interpretation, suggest that every time a measurement could happen, the universe splits, and all outcomes occur in different branches. It avoids the measurement collapse problem, but, well, it posits an awful lot of universes.
It's clear Bell's work forced physicists and philosophers to confront the sheer strangeness of the quantum world head-on. And Schneepat concludes by emphasizing Bell's lasting legacy for technology.
Absolutely. His work confirming these fundamental weird aspects of quantum mechanics, non-locality, the power of entanglement is the bedrock upon which all these developing quantum technologies are built.
So we wouldn't have the potential for quantum computers or quantum cryptography without Bell clarifying these foundational issues.
It's hard to imagine the field developing as it has without Bell's theorem and the subsequent experiments. He provided the crucial link between the deep foundational questions and experimentally verifiable, exploitable quantum effects.
So from ultra-secure communication,
driven by QKD,
to potentially revolutionary computing power,
thanks to entangled qubits,
and maybe even a future quantum internet,
enabled by things like quantum teleportation. Bell's insights are woven into the fabric of all of it.
He really stands out as a figure whose impact is still unfolding, shaping our technological future right now.
Exactly. And Schneppet makes a great point about Bell bridging physics and philosophy. His work wasn't just about equations. It forced us to rethink reality itself, even as we learned to manipulate it in these new quantum ways.
This has been a really fantastic journey through Bell's world, thanks in large part to Jorgo Schneppet's essay providing such a clear guide.
It really has. Schneppet did a great job capturing the significance of Bell's contributions.
So, to wrap up, Bell's theorem was pivotal. It confirmed the deeply non-local nature of quantum mechanics, fundamentally challenging classical physics, and, crucially, laying the theoretical and experimental groundwork for the quantum technologies that are rapidly developing today.
His discoveries are absolutely essential for everything happening now and in the future, in quantum communication, quantum computation, quantum sensing, you name it.
And it leaves us, and you listening, with a pretty profound thought to chew on.
Indeed. If the universe really operates with this fundamental non-locality, where connections can seemingly ignore distance, what does that really mean for our understanding of reality, of information, of space and time itself?
How do our gut feelings about cause and effect need to change?
Right. What new possibilities and maybe even new limitations we haven't conceived of arise from a reality where things can be interconnected in ways that just bypass spatial separation? It's a radical shift.
A truly compelling question to ponder. Thank you for joining us on this quantum deep dive, drawing once again from the excellent insights of Jorg O. Schneppet.
Thanks for having me.
Until our next exploration.